Okay, let's get started here. Um, Basically, we are talking about the software methods. And the software methods, remember, we have covered hardware, filters, amplification. And today we want to talk about the software methods. Where is the volume here? Okay. The software methods, sometimes called coaddition, and we started on this. We talked about ensemble averaging. Remember, ensemble averaging? On ensemble averaging, which is often used by many instruments, including NMR, Fourier transform, near-infrared, UVV spectrophotometry, you add data points, and that improves the signal-to-noise ratio. So, for example, here we talked about each of these data points. You acquire many spectra and then add them together, average the spectra. So that is what that ensemble averaging is all about. So ensemble averaging of a spectrum from, okay, ensemble averaging of a spectrum. So you're going to add each of the data points. Somebody?
No, I was just closing the door.
Okay. So the notice here what it say, the digital data after processing by ensemble averaging, you take all the data points, add them together. These are the dots, and then you can use an algorithm to show you the kind of spectrum, how it looks like. Okay. Individual spectra, you see, it's individual data points, and then as you from first spectrum, second, third, and fourth, then you add and then average the signals. So the ensemble averaging entails that whatever is happening during the acquisition of the spectrum, there is stability in the instrument. The analyte signal must be stable. That means the instrument is stable. So that particular analyte signal must be stable, and the source of noise is random. Then that's how you can remove the noise. These are the two requirements. And normally you want to make sure your instrument is stable. Sometimes you let it run for a few minutes, 10 minutes, sometimes 1 hour, depending on the instrument, for the circuits to stabilize. That is why we turn on instruments, let the instrument warm up, okay? Those kinds of things. So those are the things. And as a result of this, for ensemble averaging, I talked about this important equation, signal-to-noise ratio, this one here. The signal-to-noise ratio is proportional to the square root of n. That is an important consequence of this. And the reason I'm emphasizing this is the fact that you are going to be tested on this no matter what exam you take. It's a standardized ACS exam that you're going to face on 16th. You'll be tested on this. We're together there. So there will be a question on that kind of thing. And this is a result from statistics. You notice the mean value. This is the mean. You have the signal. You add, notice you're adding each of those data points. This is the, notice what it have, you're adding the spectra, and then you divide by the number of spectra or data points. So we're together there. That's just the average, okay? And that means, therefore, as a consequence, sometimes you can go into the rigor of going through the statistics of it, which I will not go. I urge you to read through it. You can see the signal to noise ratio is equal to n times Sx over then the bottom one, that is n related to the number of spectra times the square root, that is n times n. So what this means, there is a square root, the n cancels out, you have the square root of n on the bottom, which goes to the top, and that results to this, okay? This is equal to, so if you are comparing two spectra, or not, you're comparing data points acquired at different number of scans, then you would say the signal to noise ratio is the square root of n, proportional, sorry. This is a consequence of this equation. Are we together here? So without me going into the derivation, this is what you need to know. And then we said this as a consequence on how you can increase the intensity of your signals. Okay, that's what we did. We said when averaging spectra, signal to noise ratio level is improved by the square root of n in such a way that if you want to improve the signal to noise ratio by a factor of 2, it requires, let's say you have 1 and you want to increase it 2 spectra, you want to increase them by a factor of 2, then you have to acquire 4 spectra. If to improve the signal to noise ratio by a factor of 10 requires that you average 100 spectra, all right? It depends on how many. If it is 2 spectra, then you need to get 100 of them, all right? Okay, so that's what it's saying. To improve the signal to noise ratio by a factor of 10, then you need to take 100 spectra. Are we together there? So the same thing. If you have 4 spectra, it's a square, you square that number, you need to get 16 spectra. If it is 5 spectra that you have and you want to improve the signal to noise ratio, you square that number, you will have to get 25 spectra. A consequence of that, therefore, is you stay on the instrument for long or let the instrument run for a long time, okay? And that's how to improve the signal to noise ratio if you want to see that that signal is above the background or whatever signal you have, you want to increase the intensity so that you are sure of that particular signal, okay? That it's a real signal. And this is practical. You go into the lab, you get an infrared spectra, the analyte is very small concentration. And what you will need to do, you suspect there is an analyte or there is a signal due to that analyte because the analyte is in small concentration. Therefore, you acquire 4 spectra, for example, you hardly see that particular peak. You want to improve it a little bit, you took 4, then you would have to run it for 16 scans, all right? If you have 16 scans, then it's the square root of that again. Does that make sense? So you spend more time to improve on the analyte signal. So we are lucky we know instruments are, you can digitize them, let them run, okay? The problem is you spend time, and time is money, okay? That's the kind of thing we're talking about. Typically, notice what we do in spectroscopy, NMR, infrared, UVVs, fluorescence, so forth. So you acquire as many as 10 to the 4th or 10 to the 5th to observe very weak signals. This is a result of that consequence, okay? Go on. Are you stuck here? So again, this is on how to calculate the random mean square noise. You see it's related to what? Random mean square noise is related to A that is the analyte signal minus the average square. This is a deviation over n, it's a square root. This is like what we call the standard deviation. Does that make sense? Random mean square, root mean square noise. Okay, I talked about the Nyquist sampling. This is where I want to pick up from here, the Nyquist sampling. And you see the Nyquist sampling, it tells us that if you want to sample spectra, if you really want to get a good spectra, then you need to do this. You need to obey this rule. You are measuring a given frequency. Notice frequency. What is frequency? What's a frequency? How do we define frequency?
a wave function?
Yeah, but the frequency
How much time is repeat itself within a second?
cycles per second. That's what it means. Cycle per second. If you have a waveform, how many after 1 second? How many waveforms do you have? Are we together there? So that is the peaks. How many do you want given peaks? Now, notice what that equation is saying. The frequency must be greater than 1/2 delta t. Delta t, that's seconds, right? Per second, that's the frequency. Are we together there? That's what it's saying. The frequency must be greater. That is time. So that the frequency, after, how often do you acquire that particular waveform? So that is here. At least you sample twice as great as the highest frequency component of the waveform. So for example, here you can see this is a waveform from for one particular wave. Remember, you go from trough to trough, crest to crest, right? So you see, for you to pass the blue dots, that is just waveform, and then the time component is not shown there. But you notice here, this is the same kind of thing here. This particular second one, let's pay attention to the first one. I want to explain this second one here. Notice here what we are saying. If you have to sample correctly, and sampling means the instrument is going to do that for you and give you the correct waveform, the correct peaks. And we can go into the rig of that, but let's see. For example, if the frequency is 150 hertz per second, waves per second, all right, it means you need to sample the sampling rate. You need at least 300 samples per second. You will be sampling at least 300 cycles or samples per second. If you sample less than that, you get some peaks. You get information that is not very easy to interpret. What we call that, remember what we are saying, you have to get the correct waveform. Let me explain that again. You've got to get the correct waveform. That's the correct information. If you sample less than I have, then you are sampling a peak in between. It means you get a peak there, and then you get another peak in between. We call that folding over. Are we together there? Folding over, another term for folding over is aliasing. Is an aliasing. So the I want to come to that when they fold over. If you don't follow the Nyquist sampling frequency, so the custom, in practice, what you do, you sample at least 10 times of the Nyquist frequency, because it's saying the minimum you can sample the correct waveform is 2 times the frequency that you know of that particular peak. Are we together? But in practice, we go as many as 10. So that is the practice. Okay. So the consequence of this is the same kind of thing here on this theorem. So this is what I'm talking about here. If you don't sample at least twice the frequency that you want to acquire your sample at, then there is aliasing. This is very common in infrared spectroscopy, and you will see, if you don't do that, you will see peaks that fold over, and you don't know how to interpret that data. Aliasing, if the sampling frequency is less than the limit, at least twice the frequency of the frequency of the wave, then the frequencies in the original signal that are above half the sampling rate will be aliased. And aliased means, and they would appear in the resulting signal at lower frequencies. You would see some frequencies at lower frequencies, and it makes it very difficult to interpret the data. To do that, there is something we do, because these are lower frequencies. To prevent that from happening, we use a low-pass filter. Low-pass filters remove those lower frequencies. Are we together? So that's an instrument usually has low-pass filters to prevent aliasing, because you can sample less than twice, at least twice that, and you sample at a half, then you are going to have some other frequencies coming in. That appears, it makes it difficult for us to interpret what those peaks are. They are aliased, they fold over. They are true peaks, they fold over. But you want the correct waveform, you want to remove them, you use a low pass filter. Low pass filter, as you know, remove lower frequencies. Okay. That's why we do that. Okay. And this is very common. Any instrument like NMR has all these components. You would see they tell you this is low pass filters that are put into the hardware. So this is remember, this is, we're talking about the ensemble averaging, and we are talking about how you can get the correct signals. So again, I've mentioned this already. This is a repeat. Are we together there? Remember, I've talked about sample ensemble averaging. And I've said for you to do that correctly, it assumes that the noise is random. This is a repeat here. Okay, let's go here and illustrate ensemble averaging. So this is co-adding. This is an NMR spectrum. Let's say you have one scan there, and you notice in that one scan, you suspect this is a peak, that may be a peak, those are peaks. That's an NMR, just one scan. And then remember what we said, signal-to-noise ratio is proportional to the square root of what? N, where N is the number of scans. The square root of N is the number of scans. So remember we said for ensemble averaging, it's co-adding and then averaging them. So the more the spectrum that you acquire, the better. So if you have 50 scans, what you are suspecting here as obviously those are true peaks. And then here, you notice there wasn't anything here. There was nothing here. But now you see a true peak appearing there, right? Because the first diagram is just one scan and it's noisy. Sometimes you would experience this when I work with you on the infrared spectra and other spectra. If it is not, I'll tell you, acquire it at four wave numbers. Or no, everything is acquired at every 4 wave numbers. I'll tell you, acquire 4 scans. Are we together? And then if I see the peaks are not well defined, then I'll tell you, maybe go to 8 or 16 scans, all right? That means you are acquiring more spectra, adding them, you are improving the signal-noise ratio. One scan, okay, peaks may be there, but we are not so sure here. But then when you look at this region here, we were saying, okay, this particular region, see here. Now you see these peaks here. So they are being pronounced there, the same thing here. So they are pronounced there after co-adding 50 scans. And if you go to 50 scans, the better. Those peaks become this. By the way, this is, when you look at this, it's not to scale. Are we together? It's not to scale. It should be taller. All right. But what we are illustrating here is the fact that the more the scans, the better for you to see the signal. We together there? So that's what this diagram is illustrating. This is the same diagram here. And this is ensemble averaging. Remember, this is software does that. Many scans, average them. The algorithms are there to do that for you. The other one is box curve averaging. Box curve averaging is another way of dealing with spectra so as to improve the signal-to-noise ratio. Okay, so what happens here then? Notice in box averaging, again, this is very easy to understand what's happening. If you look at the algorithm itself, it's within a given box. Within a given box, you have data points in there. Let's say what box averaging does. It's a digital procedure for smoothing irregularities. It enhances signal-noise ratio. So usually, go here. Let's illustrate the figure here. In boxcar averaging, this is the diagram I'm going to show you here. I'm going to refer to this diagram or to a previous diagram, the same concept. In boxcar averaging, you take within a given box, if you have two data points, the two data points, one data point here, another one, you average them. You get a data point in between. That's what is happening. You take an average of two or more signals in some domain or within a given box. And then you plot this. So let's illustrate this so that we know what we're talking about and then talk about this. What's the consequences of boxcar averaging? Okay. For example, here, this, for example, is an absorbance data. And you see here, the data points, those ones in blue, those are the real data points. And you want to smooth the data. So what you do here within this box, within this domain or box, what you will do is these blue data points, average them, you get the middle one, the purple one, right? And then you get the next box, and you get the purple one, and so forth and so forth. Those are the boxes. That's why we call it box averaging, boxcar averaging. So what that means is you sum the data points within the boxcar, divide by the number of points in that boxcar. Here we took first, this is a simple example where you have two data points, so you're averaging two. And you do this very often. If I want to do some graphing sometimes, I do this individually if I'm faced with that kind of thing, and algorithms use these mathematical algorithms. So what is the consequence of this? You see how many data points were there? Count them. For the original data points. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, and 14. Okay? So you take a boxcar, you take a boxes or domains, and now you average them. How many do you have for the purple ones? 1, 2, 3, 4, 5, 6, 7. We had 14 original data points. Now you have what? 7. What's the consequence of that? So sometimes when you do that, sometimes the consequence of that is what we have said here previously to the previous slide. You lose some detail in the overall signal. We're trying to smooth it out. This is the drawback of a boxcar averaging. And I've seen an ACS exam, for example, they will test you on this. We're together here and expect that you will remember these kinds of things. You will do an ACS exam. Put it together, final exam. So make sure you know these kinds of things. Sometimes they want to throw these questions at you, and then they expect you to remember signal averaging, boxcar, ensemble averaging, boxcar averaging. This is why I'm taking my time to go through this for you to understand, so that you don't say, well, I don't know what this question is asking me. Are we together? Okay. And any sort of questions, you would have these kinds of questions in anywhere that you might be faced with. Okay, that's that. And here is the example from the textbook. Remember, it's boxcar averaging the same kind of information. So within a given domain, two of them, you take the middle, that's the middle one. And for this one here, you will see, again, for these two, you then have the middle data point. Then this one here, you notice you are averaging those data points up here, and so on. In general, you notice you have fewer data points. You are missing detail. And sometimes detail is important. So when is it that you will not lose this? The assumption for the boxcar averaging, we have said it's useful for smoothing irregularities and enhancing signal-to-noise ratio, assuming that the irregularities are not the result of noise, this random. And the assumption is that the analytical signal varies more slowly. That's when you can use this, more slowly in time than the noise components. And in practice, for this to work perfectly without losing much detail, in practice, 2 to 50 points are averaged. So in order not to lose so much detail, the more the better. 50 data points can be averaged to a final point. And you must be careful when you are doing this. Notice what it's saying. You must be careful not to adulterate the real signal. Because sometimes when you average these signals, you might get a spectrum that does not look like the original. Does that make sense? So hence, you have to be careful that the number of data points you are averaging are reflective of the original. So that's important. Any question here so far? Okay. So again, this improves the signal-noise ratio, and you can see what we are saying here. For every 2, you lose 1. So the signal-noise ratio, you have improved the signal-noise ratio, and it's proportional to the square root of the number of data points in the boxcar. Does that make sense? We used an example of 2. If 2, you have lost 1 because you have averaged them, right? So if it's 3, you have lost 1, okay? So you lose those kinds of data points. So again, without overemphasizing it, there's a significant loss. This is a significant loss of information will be if the length of the boxcar is not comparable to the data acquisition rate. It's best to implement boxcar averaging with sufficient data points. I think I've said enough of that, right? It's important. The more the data points, and it's reflective of it's reflecting the true data points, then you can average them. You don't lose much information. And we are lucky because the instruments do this all the time. Okay, this is software, because there is the question that I gave you on Friday. And here, this is from LibreText. How many of you use LibreText? No LibreText? Nobody knows LibreText? My. LibreText is, you can enter LibreText, right? LibreText, professors come together and write to make it easier for people to understand what the information is. And so I pulled this from there. You can see if there is a given topic, you can go in there and read it 2 pages, 3 pages for that particular section. So it's a good way, but sometimes they don't have correct information. sometimes, okay. But in general, it's these professors like me who teach the course and go in and try to simplify it. So this is from LibreText. So notice what is happening. The y-axis is a signal in microvolts, and the x-axis is time. Notice what we are doing. Again, we are talking about boxcar averaging. There's a signal here, all right? There's a signal here, seems to be a signal here. So every data point, you average them, you get a data point, okay? You keep averaging them, you average the second one. You might lose all your data points. That's the point I'm trying to illustrate with this. You can see what that means. You go to the next slide, that 2 5 microvolt signals, the peak at 1 minute, 1 minute, see this peak here, the 1 minute. So if you want to measure here, it tells you what that height is. So that means that peak at 1 minute with a width, the width is at the bottom of 0.04. And then the peak at 2 minutes, see there is a peak at 2 minutes again. It has a width as well. And so when you do this, when you at 2 minutes with a width of 0.4, you see it's a little bit broader. So one is 0.04, the other one is 0.4. And then what is the consequence here? You can average the boxes, and at least you're going to smooth it out. But the middle set, usually, you notice what is happening? The bottom data set, the theoretical signal-noise ratio is 13. There's no smoothing, right? Then the second one, the middle one, you look at the middle one here, that peak at 2 minutes, you smooth it out by doing boxcar averaging, And you notice the theoretical signal to noise ratio is about 29. You can go in and look at it, 5-point box curve. And now, notice what it was. Now, it is 0.05 minutes long. What was it before? The middle one was 0.4, right? You have reduced it. You have lost the information that the top set again. You notice that there is some distortion that occurs. And that's the point of me using this. You've got this information. Okay? So I want to go next to an important concept here. We have talked about ensemble averaging, that's digital, and so is box averaging. Then there is Fourier transformation, FT, IR, FT, NMR, FT, whatever. We use this all the time. So let's talk about Fourier synthesis and the Fourier transform. This comes from math. FT. Have you covered this in math? Fourier transform or Fourier series. We have the various series that you cover in a calculus class. So this is Fourier, the person who came up with C series. Once you understand what it is, then it's easier for you to know whatever you know. I present this for you so that you know what's really happening with some of this. I want to hurry up so that we do the instrumentation. So this was Jean-Baptiste Joseph Baron Fourier, 1768 to 1830. How many years did he live? 30 plus 30, 62. And he made a change in our lives. Okay, some of us live longer and we hardly make any impact, right? So look at this. This person here, French person. So this is the Fourier transformation. He says this, any series that you get, any periodic function, because we measure peaks, we measure signals, spectra, chromatograms, any periodic function, no matter how trivial or complex, can be expressed in terms of a converging series of combinations of sines and cosines. Are we together? And here it is then. That's the Fourier series. So you have a periodic function, therefore, it's a sum of discrete sinusoidal functions, sines, right? So here is what he came up with down here. You want to see, so you want to see down here. This is a function of x, 1/2 a naught, that's at the beginning, time plus the sum of n equals to 1 to n equals to infinity. And then you have an cosine n pi x over t, that's the periodic time, plus bn sine n pi x over t. And you know, if it's a periodic function, it's going to repeat itself every so often. So this is, and you can decompose this function into two functions, the sine and the cosine. So you can decompose it into these two functions. One will be the cosine part, the other one will be the sine part. That's what that is. Does that make sense? So in other words, that is at the heart of any Fourier series that we deal with in instrumentation. So then let's now go to what this, a consequence of this. This is a square waveform, and you will see this waveform from minus 2 pi to 2 pi. You know, 2 pi is what? 360 degrees. So from minus 2 pi, minus 360 to 360, it's a square function. And you can read about it and see this is implemented in instruments. But I want to go here this is what I want to do to make you aware of how this is carried out, because this is also tested here. Usually, you acquire spectra with time. So that time is in the time domain. The spectra is within the time domain. So we need to transform the spectra acquired from the time domain to the frequency domain, because we're interested in the spectra. So the procedure for Fourier transform that is in instruments is we have a time domain, convert the spectra in the time domain with all the data points. It's in the time domain, you convert it to the frequency domain. So that is how we do it. That's how the instrument does it. So how is that done? You have a low pass filter. We keep talking about these low pass filters. So the low pass filters will remove the high frequency. The low pass filters usually will remove the low frequencies and put it into the high frequencies. Does that make sense? That's what we do. So it's going to remove the noise region. And then notice once you remove the noise, then you do FT. That's why it's called Fourier transform. What's Fourier transform there for? Obviously, it is just changing the spectrum from the time domain to the frequency domain, use low pass filters, and then from there you do FT. FT, this is inverse, FT or inverse, this is the inverse. So again, I want to show you what the inverse means, the FT inverse. The Fourier information is just transform time domain to the frequency domain. That's Fourier transform. And you can do vice versa. And then this is it finds usage in FTIR, FTNMR, and you need fast computers like we do. We enjoy fast computers. So let's illustrate this class on what we mean by the two terms. So HT, this is the spectra in this illustrated here. Notice here on the blue, this is HT. You acquire spectra in the time domain. You FT this spectra. You FT the spectra, that means Fourier transform the spectra into HF. HF is the spectra in the frequency domain. Are we together? So let's look at this one here. Now you're going to see here what this is. This is a waveform in the time domain. This one here, the sine pseudo wave. The instrument will transform this, Fourier transform it, and you get one frequency. Does that make sense? This is what it does in the instruments. Now, the same thing here. You might see a noisy spectra. You use filters, more or less like that, but then you will transform it, FT. It might have two peaks. That's what we see, like NMR. Okay? So again, it might be in this form. Again, if it's a square wave, then you transform it, it may have several peaks. Does that make sense? So in other words, the one on the left-hand side is in the time domain, as you will see the wave, but then you put the filters, and then it removes the noise, and then you get your real frequency in the frequency domain. Okay, I think that is the point. I've made that point clear, and you will see this is in Fourier transform. This is a process of obtaining the spectral frequencies, HF, comprising a time-dependent signal, HT. So the spectra and the time signal is changed to the spectra into the frequency domain, and the whole process is what we call Fourier analysis. Okay, so inverse, if you do, that's normal Fourier transform, and then inverse FT, it means you change the spectrum from the frequency domain to what? From the frequency domain to the time domain, to what it was. And you can carry on. This is, for example, again, it's cosines and sines. It's the inverse, and that is a mathematical function there. Okay? Then you're changing the frequency, the spectra in the frequency domain to the frequency in the time domain, small h sub t. Does that make sense? I am not going to those details, get those mathematically or a physics class, or if I was dealing with signal processing class. So that's all we want to understand, the concept, all right? And so that is then important. Okay, and there are other algorithms. This is again Fourier transform. Let me go to the heart of this. We have talked about all this. There's nothing new there. The advantages of moving average. These are other Savitsky-Golay algorithms. These are mathematical algorithms. They use least squares, and if you're dealing with XRD, it uses this. I'm not holding you responsible other than for you to know there is such an algorithm. Are we together there? Yeah. So it was an old algorithm. I wish I could talk more about it, but that's fine. Now, I want now to go to emphasize something that we dealt with in the lab. Do you still have within the last 5 minutes? I gave you this in the recitation. It's okay. You have another copy. All right. That's good. Let's pass them on. So I now want to be sure that we understand which question first. If you have it, that's fine. It's on under the recitation. Okay, you prefer that. Anyone prefer the hard copy? Okay, let's go there to have access to recitation number 2. It's fine. I want to make sure I clear any confusion that we may have over this. And you should be able to answer these questions comfortably and fine. Follow along. See, this picture here is an illustration of how we go about it so that we are sure. Number one, this is a typical question like I've given you. And remember, here you have this is the baseline, okay? And above it's a noise, and then there is a signal here, and there is the middle of that signal. You will see here, you can compute this using Excel. You have the baseline is at 60. You see that? You can read the baseline is at 60. That's that baseline. And then the signal starts at 50. This is where the signal starts. So the signal starts at 50, but the baseline is here. And then you have the signal ends at 150. The signal is about 150 here. This is where the signal is, but it goes above as well. Then you have the signal size and 100. The noise, standard deviation is 20. It's been computed. You can compute this. Now, notice what we are saying here. We use a factor of 5. Where is that 5 I saw? You see where you divide by 5? Where are we divided by 5? Which line? Okay. So usually, right here, you can see this? The max minus the mean divided by what? 5. Why do we use 5? Let me go through this. I want you to get the hang of how to do this so they don't get confused, because some of us, we want to be clear on this. So the first thing we know why we do signal averaging. One advantage for signal averaging, you have multiple spectra that improves signal noise ratio. And this is from Harris. The signal averaging usually can improve the quality of your data. So I want to go through this and illustrate this example here. This example here, notice, remember the picture I've presented to you where you have the baseline and so on, okay? Notice this. This is a signal here. It's from figure 2030 of Harris, what do you call that book? Quantitative chemical analysis by Donald Harris. So that chapter. So notice this is how many? We have each of these are spectra, like we have said, 1 spectra, 4, 16, 64, 256, and so forth. And so notice here, this is the noise. Can you see that? You want to measure, that is the noise level. So in this diagram, you have to measure that. Does that make sense? So that's how you measure the noise. And then the signal to noise, you measure, where do you measure it from? I want to make sure you know. Note that a single spectrum contains a good deal of noise. an easy way to measure noise is to measure the range of noise on the baseline. So this is the range. That's where you measure the noise level. And then what you now have to do is the following. The signal is measured from the middle of the baseline. Are we together there? We want to be clear. That's why I'm putting this. The signal is measured from the middle of the baseline. See this illustrative example. This is the baseline here, the middle, and this is the signal. You measure it from the middle of the baseline and to the middle of the noisy peak. So this is the noisy peak here, if we use this first one. So the peak apparently is here. You can see there? So, and then it goes here. So the middle, all right? Does that make sense, class? So you want to follow this so you go to the middle of the noisy peak. The peak starts from here, as you can see. That's where the peak, the analyte peak, and then it goes here. You go to the middle. This is where you measure it, the middle. Middle of the baseline to the middle of the peak. Then the one we have is not so noisy, but you can estimate it a little bit. We're together there. So you know the noise level. And then in this case, when we measure this has been given to us, no units there, but you can see these are 9 units here. And then when you measure from the middle to the middle of this baseline, that's the signal. And here we are given in this example, it is 14 units. Does that make sense here? So we already know the two. That's the signal to noise ratio. Okay? So in that case, therefore, in this case, the signal is 14 units and the noise is 9 units. And therefore, the signal to noise ratio, you want to see, the signal to noise ratio is 14/9. Does that make sense in this example? So we want this to be clear beyond a shadow of doubt. Okay? Oops. Time this clock is. Yeah, we have 2 minutes left. Let's use that clock. What we have. So that we know how to do this now. Let's keep moving here. This is all we know. And therefore, in this case, notice we know how to calculate signal noise ratio. Are we together there? All right. In the case that you have, because the peak is not well defined at the top, you can even measure from the middle to the top. Does that make sense? You can do that because it's not so noisy. Does that make sense, class? Okay. The middle one you can see. And you notice that it starts from 2. It's actually 1 there. If you take, you can take the middle of that. If you read that, and then you can measure the baseline to the very top. So now, here is something crucial that we need to be aware of. The RMS, root mean square noise, is about 5 times the peak-to-peak noise. That's why I used 5 last time. It's usually taken as 5. Okay? You can do the gory details, but you can use 5. So that simply means here, if it's about 5, see the first one we said, for this one, the root mean square is roughly 9/5 because we use the 5 times as the noise. This is normally, all right? And that means this example is illustrating the fact if the number of data points is large, the root mean square noise is the standard deviation of the data points. If it's large, we're together there. If it's large, then how do we calculate that noise? We take the root mean square noise as 5 times the peak-to-peak noise. And you would see that if you have a large data points, then you have a different signal to noise ratio. And that's the point that I wanted to convey to you today. Clearly, the signal noise ratio depends on how you measure the noise, if you have a large or a small, and then you can compare the two. So I think that is that's the burden I had in my heart. Okay, is that clear now? A little bit. Go over it, And that brings us to the end of this chapter. On Friday, I start on chapter number 2. No, not number 2, chapter number 6. All right, on spectroscopy. All right, have a good day.
Thank you. How the attendance this week?
No, I did not pass the attendance. No, you're not turning it in. That's the, okay, thank you.